Sharding is when you split your database across multiple database servers, right? So where you have one database, and now what you are doing is you are splitting your database across 3 shards. These shards are actual physical database servers. So you have taken your entire data, you have split it in some way across 3 separate machines to very well handle the incoming load. So in vertical sharding, what we are doing is we are distributing the table across multiple shards. Which means, let's say you had one database which had 4 tables, T1, T2, T3, T4. Now, you are splitting this database into 3 smaller shards. First shard is responsible of handling table T2. Second shard is responsible for handling table T1 and T4. Third shard is responsible for handling table T3. So this way, with the focused set of tables, you are keeping them together in one database. Classically speaking, this comes in very handy when you're transitioning from monolith to microservices. Sorry. And another reason for us to do vertical sharding is, or to do this table movement, is to basically better manage the load. For example, if you kept a table T2 in this, or rather, if you have one database which is, let's say, shard 2, which handles table T1 and T4. And there is a lot of incoming load coming in for table T1. So which made your database server 2 or your shard 2 very hot, which means it is not able to perform at its full capacity because it is constantly under pressure. So to better manage the load, what you would want is, you would want to physically take one of the table. Let's say you took the table T1 and put it into another shard which is not so under pressure. Let's say you took the table T1, moved from shard 2 to shard 3. To reduce the load or on shard 2. Right, so this physical movement is made very simple when you have scripts handy. Right, so obviously this is not just theoretical, we actually implement this. So what we'll do is, in this video we'll talk about how to actually implement vertical sharding. And it's not difficult, it's really not difficult, but how do we actually implement it? So the core problem statement here is, you have one database which has multiple tables. What you want to do is, you would want to spin up another database and move one of the table from this database to another database. You can extend this to move multiple tables, but the idea still remains the same. So the problem statement we operate on is move one table from one database server to another database server. How do we do that? Right. So before we directly jump into the moving part of it, what we definitely want to do is, we would want to store meta information. Like for example, what you'll have is, given that now after you do vertical sharding, you'll have multiple databases handling multiple tables. So now when your API server, when you get at the end, you'll get some user request coming onto your API server. How would your API server know to which database server should it connect to? For example, if your request is coming for authentication, you need to talk to authentication database servers which has those authentication related tables. Where would we store this information? And this information should be stored in a very secure way, not just from a security perspective, but more from the consistency perspective, where every single one of your API servers should get a consistent view of it. Right? So that is requirement number 1. So where do we store this meta configuration? That hey, these tables are stored in these databases, so that my API server will have this information from this source or this configuration, that hey, if I want to query an authentication table, let's say authentication users table, which database should I connect to? It will get from this meta configuration, and then it will connect to that particular database server to read the particular information and send it back to the user. So we need to store this information somewhere, and this has to be a consistent view across all API servers. So it cannot be stale. Second, now that we would be moving the table from one machine or from one database server to another database server, this configuration will have to be changed. So in the mapping that we stored, that this table is present in this database, after we move the table, this configuration needs to be changed. That hey, now this table is present in another database. For example, table T2, which was present on database 1, is now moving to database 2. When this configuration this configuration will be changed. And once it is changed, what we would want is, we would want this information to be reactively sent to all API servers. Which means that otherwise what would happen is, you have changed the configuration, which means your table has moved from one database to another database, But what if your API server doesn't know about it? If API server doesn't know about this movement, it would continue to connect to the old database server, which is wrong. So that is where we would want this information to be reactively sent to API servers. So that's why we would want a tool that solves these two problems for us really well. First of all, storing meta information and being reactive in sending out updates on what altered. So that is where the one tool that fits really beautifully well over here is Zookeeper. Zookeeper stores this exact same, or Zookeeper is meant to solve this exact same problem. So what Zookeeper would do is it would hold the meta information. Meta information like table T1 is present on database 1, table T2 is present on database 2. Right? Something around that, it would hold this information. And if anyone changes the configuration on Zookeeper, Zookeeper will proactively send updates to all the three API servers. So Zookeeper has something called as watch. So you can watch a particular configuration, and if that configuration changes, the watch function on your API servers will be triggered, and in that they can fetch and query and get the latest configuration, and immediately that gets updated. So this way, instead of your API servers proactively polling, hey, is there any configuration change or not, we are making these things reactive. So the idea here would be, whenever an API request comes in, it comes to our API server. API server will have the copy of configuration from the Zookeeper. It would be kept in sync. API server will know which database server to talk to. It will talk to that particular database server, compute the result, and send it back to the user. Any configuration change happened in Zookeeper, it would be proactively sent to all the three API servers. So Zookeeper is not just acting as a configuration meta store, but it is also acting as someone who can proactively broadcast or proactively send the updates to every API server which is connected. So this way, whenever we alter any table from one to another, we update the configuration, the information will be proactively sent to API servers, which can can start connecting to a more relevant database. Right, so this is where Zookeeper comes in. Now let's talk about how to actually move tables from one MySQL server to another. Here I'm taking example of MySQL server, but the steps remains the same no matter which database you pick. So now what we have to do, let's say we have tables T1 and T2. Both of them are present on database 1, so DB1. And what we want to do is move table T2 from DB1 to DB2. So what are the exact steps of us doing that? Step number 1, we dump the table. First of all, whenever we are moving table from one to another, what we would want to do is we would want to dump this table locally and then upload this table into some another database. So that is exact step number 1. So if you are using MySQL, you can leverage a utility called MySQL dump. It's a official utility that is provided by MySQL, with which you can literally dump the table into various format like SQL, CSV, various format. Most of the people prefer SQL format. It dumps the table into a simple SQL file locally. And what you can do is this file would also contain the position of the bin log. So what is bin log? Bin log is your basically commit log, where every single operation that happened onto your database gets logged into this bin log file. And it also keeps checking, hey, in one transaction, when you're invoking MySQL dump, in one shot, it would take the entire dump of the table and mark that, hey, in this bin log, I've read till this position. So it would take all of this information and dump it into a SQL file. Now, why this why this is important? So what happens is bin log is the one where you have all the operations that ever happened onto your database logged sequentially. And when you have this information there, you'd need to know that, hey, in my dump, I have information till this point. So that when you create a new database, it can start reading after that position. So bin log position is extremely important to be logged, and which is where MySQL dump as a utility comes in very handy. So you basically took the dump of your database into a SQL file and which also contains the bin log position. It contains both of this information. Now step number 2. You took your dump.sql file and loaded into your DB2. So your DB2 was the one where you had to move your table. So you dump that table. So in the first step, we dump the entire table along with the bin log position on your local machine, supposedly on your local machine. And now you are taking this dump from, and now you're taking this dump and applying it onto DB2. So when you restore this dump onto another database, this is not entire database getting copied, this is just that one table which is getting copied, or one table which is getting created and the row getting inserted on that. Right. So now after this step, you have DB2 with that one table with that entire data up till the time when you took the snapshot, when you dumped it. Till that point it has everything. But obviously what you would also have is your main database is still accepting writes. It is not down. Your main database is still accepting the writes. So the new entries would keep on getting added in bin log. New updates will be made onto the database. So now what we do, once we restore the table onto another database, let's say DB2, what we have to do is we have to start a replication. So that's where you can write a simple replication job. There are a lot of utilities out there that does this, where what you will do is you will read the updates from DB1 for that particular table and apply them onto DB2. This way, your DB2 had the old data till a particular time from the snapshot that you took, and then all the recent inits that have happened on the DB1 while you were doing this will also get replicated to DB2. This is an explicit job that you will write. You, in most cases, you will not be able to use the MySQL's default replication because there are some extra steps or extra checks that you might want to apply, filter out some things and then apply. So you might not be able to use a default one, but that's where a small replication, there are tons of utilities out there in every language that you can think of. So you can use that, which would basically read the bin log from the position, and that is why the position is important. Let's say we snapshotted a bin log at 156th position, which means up till byte offset 156, I've consumed everything, or up till byte offset 156, everything is part of my dump.sql file. So now when I'll start the replication, I'll start reading from line 156. Right, so post 156 offset, I'll start consuming all the updates that happened. This way, all the incoming writes that are happening on DB1 will then start replicating onto DB2. This way, eventually, the two databases DB1 and DB2 for that one table will come in sync. Right, will be very small difference between them. The replication would be constantly happening. Right, so this way we have ensured that on our DB2 we took the snapshot of table 1, loaded it, and now replication has begun. So that now DB2, the table T2 on DB2, the table T2 on DB1, they are both in sync. So once we know that they are almost in sync, this is where you have to do a failover, or not really failover, but a cutover, where you have to stop the traffic on DB1 and move the traffic to DB2. So how do we do that? So what we do here is we know that if the replication lag between the two databases for that table is very low, let's say it's literally 0.00001, something like that. You'll see that number in the statistics. If this is very low, what you'll do is you'll do a cutover. When you do a cutover, what would you do? You would want to stop the writes going for the table on DB1, and you would have to start taking writes on DB2 for the table 1, reads and writes both. Right? So now what you will do is on DB1, you will rename the table. As soon as you rename the table, any incoming queries that is coming in for that table, it would give you table not found error. For example, you had table T2 on DB1 and you changed it to T2 underscore BAK, basically T2 underscore backup. If you change it to that, the incoming queries that are coming for that table for T2, that table does not exist. And rename operation is atomic. It's very fast. So that's where for that duration, any incoming request for table T2 on DB1 will fail because it would give you table not found error. Then basically that is popular. That is exactly what we want. We want to stop the incoming writes onto this database, for this table. And then what we do, the next step is you update the entry in Zookeeper. Remember Zookeeper for all the configuration? So in Zookeeper, what we'll say is we'll specify that, hey, now table T2 is present on DB2. Earlier the entry was table T2 arrow DB1. Now the entry would be table T2 arrow DB2. So when these two steps are to be done manually, right? So some developer, a script is executed manually or something, because you have to monitor what's the replication lag and is this the correct time or not. This cannot be done easily automatically. So that is where someone has to do it manually. So when that changes, you update the entry in Zookeeper. For that duration, you will get table not found errors. But as soon as you update the entry that now table T2 is present on DB2, Zookeeper, as I said, reactively sends information to all API servers using watch. As it sends information to API server, then any new incoming request coming in for table T2, because you updated in Zookeeper, Zookeeper proactively send that information to API server. API server will now start connecting to DB2. Right. So for that small duration, for that small time window, when you were renaming the table, updating the Zookeeper and the updates reactively going to the API server, for that duration, you will get table not found errors. Otherwise, everything would work just fine. Just fine. So the overall flow, or the, not really an architecture, but overall flow to do vertical partitioning would look something like this. You will have your users who is constantly sending you reads and write requests. The read and write request going through load balancer, hitting one of your API servers. API server, let's say it's an authentication request. So API server would know where authentication table lies in. How would it know? Using Zookeeper. So Zookeeper, what it would do is, Zookeeper will have all the meta information with it. So table 1, table 2 present in database 1, for example. All the tables are present in database 1. And then API server would know which database to connect to. It will connect to that database, fire the query, get the response, and read back to the user. That's the happy flow. Now, you would want to move that table from one database to another database. Let's say table T2 from DB1 to DB2. So that is where your partitioning service comes in. This is normal script that you wrote, like just naming it funky, but it's just a normal script that you have written that does all of this part, and an engineer of yours is doing it, right? Nothing fancy, like you yourself are doing it. Right, so just naming it something just to give itself an identity, nothing more. So the partitioning service would kick in, and what it would do is the exact 4 steps that we talked about. So this is not at all theoretical, actual practical. This is exactly how it is implemented in industry. Right? So engineer then fires this thing, moves the table, like doing that MySQL dump, restoring it in another place, starting the replication, where the two databases, that one table across 2 databases getting replicated. When the replication lag is 0, you do a cutover. As soon as you do a cutover, you fire the update onto Zookeeper saying that now table T2 is present on DB2. As soon as the configuration is updated on Zookeeper, the update is sent to all the API servers. The newer requests that come in will go to that corresponding database. So newer requests for T2 will go to DB2 instead of DB1. And this is how vertical partitioning is actually implemented. So here, if you would have seen, because we have a small time window where you will get table not found errors, right? Because when you are updating the Zookeeper, or when you are renaming the table in DB1, updating the Zookeeper, and this update is getting sent to API server for that small time window, hardly 5 millisecond, 10 millisecond, at max 15 millisecond, not more than that. For that duration, you will get table not found error, so your writes will be affected. So what does this mean? This means that we are preferring consistency over availability. We have given up on availability for some time, but we have made our systems consistent, which means that we not be like that some writes that are there during the downtime that are gone, but all the writes that happened will eventually propagate with replication lag will almost 0. It will immediately catch up, and you'll have a very consistent view of data no matter what. The approach that we discussed works for small to medium size, even to some extent large size of table, but huge tables will be problematic with this approach. So that's where with huge tables, you typically don't migrate huge tables. You take smaller tables and put it into different shards, keeping huge tables intact in one database. The reason why that would be a challenge is because because if a table is huge, it means it is taking large amount of writes. If it is taking large amount of writes, your DB1 and DB2 for that huge table might never come in sync, or the replication lag would always be there because it is taking that many or that much of writes. So whenever you are moving one table from one database to another database, you would typically want to move it, or you would want to typically move small or medium sized table, or instead of moving a huge table from one database to another. Right. So this is just one minor caveat that we have to remember whenever we are implementing vertical sharding. And again, everything that we discuss is not at all theoretical. It's exactly how we implement it. You can very easily mimic this entire thing locally, and I would highly encourage you to do it. Just run a small instance, just run a small process of Zookeeper, have two MySQL server running, one on 3306, one on 3307, write its script, take the dump, note the bin log position, write a replicator. It's very simple, but you'll get a very solid understanding on how it is actually. It is very fascinating on the kind of tactics companies has to apply or products has to apply in order to ensure that we handle the scale that we want and business survives, right? These are few of those gems. And I love this approach where you see the micro decisions we took, the exact granular steps that we went into so as to implement vertical sharding. So nice. That's it for this one. I hope you learned, like you understood that vertical partitioning is not just theoretical. It actually happens in real world. I showed you a practical example, the exact way it is actually implemented in real world. So I would highly, again, I cannot stress this more. Go and implement this locally. It is not at all difficult. You will learn much more than just watching this video. Right. So nice. That's it folks for this one. I hope you found this interesting, amusing, and you learned something new. If you did, give this video a massive like. So again, if you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week like this one. And I'll see you in the next one. Thanks a ton.